All right, so in this most wonderful edition of ENGR 425, I think it's section V, that we are in. We've wrapped up isentropic and adiabatic relationships, yes, last time. And we're going to move on to compressible flow phenomena today. But before we get there, what is isentropic flow again? What defines it?
There's no change in entropy from point to point.
That's a true fact. What about the assumptions that are part of it? What things have to be true? Do we have to be able to say anything about like heat transfer or stuff like that?
So is that where the adiabatic part comes in with no heat transfer?
Correct. Yeah, because like in pull this over to here. It's called if we look back at relationships from thermo, one of those relationships is the change in entropy is equal to what delta Q over T. So for an isothermal whole process, the change in entropy is directly proportional to the amount of heat entering or leaving the system. So in order to have isentropic conditions, it's implicit that we also have adiabatic conditions. What was the other thing that was kind of an important deal?
Didn't we say that it was steady flow?
We've been dealing with steady flow, but isentropic flow doesn't have to be steady.
So with isentropic flow, well, within the flow, isn't it homogeneous?
We've been assuming that the flow is how do I say this? That the flow on either side of the shock is homogeneous to distinguish it from the shock itself. But I mean, like we came up with all these isentropic relations. So if a flow is isentropically compressed or expanded, it'll follow those relationships, which, as a matter of course, also means that you can have an isentropic flow that has different pressures, temperatures, and velocities and such in it. But if you look at the energy equation that we have here, so if we ticked off this guy because that's our adiabatic assumption, right? What else might be what other things in here might cause might cause a gain in entropy? Does friction do that? Yeah. Why? Why?
Friction would be heat loss.
It evolves heat, but it's not heat loss in and of itself. Like you're not transferring heat to the outside environment. You're doing work in the outside environment and such like that. But maybe the better way of thinking about it is that in order to be isentropic, you have to be both adiabatic. The process has to be adiabatic, and it has to be reversible. Now reverse friction effects.
No, so that would, yeah.
Yeah. So that gets rid of any viscous terms in here. We got rid of the last one because not because of what's called an isentropic thing, but just because we assume that body forces, so y, I promise, were equal to 0. Okay, we on board with that?
Yeah.
Sweet. All right. So isentropic processes are both adiabatic and reversible. It implies that it is an inviscid process, as well as one in which there is no heat transfer. We additionally assume that there are no body forces. So it kind of simplifies the expression a little bit more, just ignoring EM fields, gravity, all that jazz. Great. All right. So by using those and assuming steady flow, we got ourselves some isentropic relations as well as some stagnation relationships, or total condition relationships, where we related total pressure, total temperature, and total density to Mach number. So based on the incoming flow, if I isentropically slow that flow down to 0 speed, I can figure out some relationships between pressure, temperature, density, et cetera, et cetera, et cetera, between the free stream and the stagnation point. That does, of course, assume a calorically perfect gas, which is. What is a calorically perfect gas?
Calorically perfect glass. Yeah, glass. That'd be something interesting. Gas is part of that.
Absolutely perfect in every way.
In some ways. In the adiabatic ways. So if you add, it means that the CP/CV is that of an ideal gas, right?
It's called, so a perfect gas is one that you can treat as an ideal gas. A calorically perfect gas is one where I think you're hitting all around it. A calorically perfect gas is one where the specific heats are constant.
Mm-hmm.
So your value of CP and CV you treat as a constant because their actual variations are relatively small over the range of expected temperature variations, which for us is pretty much anything under 1,000 Kelvin. So, cool. All right. So that's that. What I want to look at then is if we've talked about kind of what, there we are, kind of what some of the effects of going compressible are, maybe we can look at some of the more visible effects. So the 3 images we got here, these are either Schlieren, which is what we looked at first day of compressible flow. So variations in color, black and white, with the exception of where a thing is, like right here or here. Variations in color are variations in density. It's really variations in the second derivative of density, but we'll use it as a proxy for density here. Hello, Koi. And this the one with the airplane in it, that's what's called a shadow graph image. It's kind of like if you're looking down the down road and you see a mirage, you're seeing density variations too. If you see like the like shimmering bubbles of air, if you will, that's more or less what a shadow graph image is. It's more like a backlit Schlieren image, usually which called where you're looking at a background and seeing the density variations on that instead of by a Schlieren method. I think Schlieren supposed to be more sensitive, but shadowgraph can be easier, especially for larger objects. Or in the case of the T-38, it was flying at the time at like 20,000 feet. He hit above ground, so hard to make a Schlieren setup in that location. So, what did we say that these dark lines are?
Will that be high density change?
Yeah, so those are regions of obnoxiously high density change. There are some smaller lines like here. You can just barely see them around here where you're getting some density change. Those are and that's non-negligible. But the highest density change is where that darkest, most defined line is. You can see it on the T-38 as well. That's the kind of airplane this is. So that's where the greatest change occurs. And you see it has some thickness, not much, has some. And this is what we're going to call a shock wave. So it's a very thin region where you get intense variations in density. If you get intense variations in density, it means the pressure and temperature are also going to jump as well because of ideal gas law relations. So we can expect the flow on this side to be one thing, flow on this side to be something completely different. We also can see, let's just keep focus on these two guys for right now. You can also see some pretty serious differences in how these shock waves form. Like, what's the difference between this kind of blunt-nosed guy here and the T-38? Is there any difference in the shock waves, how they form, and kind of how that relates to the shape of the body causing them?
Oh, with the jet, it's more of a pointed. Oh yeah, that's what Corey's saying. The rounder shockwave from the rounder point.
Yeah, it's called good. Yeah, it's called both you got it. There's a direct relationship between the shape of the body causing the shockwave and and kind of the geometry of the shockwave itself, which is kind of interesting. Like the T-38, like you say, has a very sharp nose here. You can see that, and as a result, the shockwave it's very angular, or it's almost a straight line, and coming off of the nose of the vehicle. However, if we go down to this kind of blunt-nosed object here, I want to say that this was this is when they were testing out shapes for the Mercury capsule, Mercury or Gemini, I forget which. I think it was Mercury. This was one of the shapes. This end of the vehicle would be pointing down into the atmosphere as it made its reentry, and it's a much rounder shape. And you see this very rounded shockwave coming off of it. It's also not the shockwave also doesn't touch the vehicle in this particular case. I can go up here to the T-38. And the shockwave is coming pretty much from the nose. Here we have what's called a detached shockwave, where the shockwave is happening some distance in front of the vehicle itself. Okay, so that's some kind of cool stuff. If we look a little bit closer, we might even be able to categorize these shocks a little bit, like. Here on the T-38, the aircraft's moving straight through the air, right? It's just going forward. So the air by consequence, if we think of it as if we think of what the free stream might be doing, the free stream's coming straight in, right? So that means that the free stream is approaching that shock wave at an angle. So that's a characteristic that we can think about. Because if we go down here to the blunt body, we have the free stream coming in straight again, right? Depending on where you are along the shock wave, the angle between the free stream and the shock wave is going to be different. In fact, when you're right in the middle here, it's almost zero. It's called the shock wave and the free stream are almost perpendicular to one another, which is kind of interesting, as opposed to out here where it's much more akin to the shock wave and the free stream conditions in front of the T38, where they're meeting at some angle to one another. So we can kind of keep those two in the back of our heads as things we might want to look at later on, or ways we might want to look at shock wave flow interactions later on. Any other comments about those two guys, about the T38 or the blunt body there?
Nah.
All right. Well, let's go over to the really wonky one. This is an airfoil. You can just see the dark outline of the airfoil here. Should not use dots. You can just see the dark outline of the airfoil there. I'll try to color it in a little bit. This guy here, and this guy's a little bit different than the other two. There's no detached shock wave in front of it. There's no attached shock wave coming off of the nose. What's going on here instead? Like before, we have a shock wave. We have actually a kind of interesting shock wave structure, actually, but it's coming off of the middle of the airfoil. So one thing that we kind of could imply from up here is that shock waves are related to the fact that there's a thing in the way. And you have a supersonic flow. It hits it, it comes into the thing and makes this shock wave. Here, there's a thing in the way. There's an airfoil, but there's not a shock wave occurring where we would expect it to be. Meaning, if this is the nose of the thing up in front here, we don't see a shock wave. So that means that our flow is probably subsonic when it comes onto the airfoil. So why would we get a shock wave on top of this thing if the free stream is subsonic?
Because it accelerates.
Okay, cool. Right, we know from our incompressible flow analysis that flow should accelerate as it goes over an airfoil. Great. So if we're at a high enough subsonic speed, the flow might accelerate to become supersonic, and then maybe sometime after that, it generates these interesting shockwave structures. But let's look at this a little bit more closely. So we're getting an idea that supersonic aerodynamics might be a little stranger, but if we look at it a little bit more, on the left here is a subsonic. This is a subsonic airfoil. So free stream Mach number much less than 1. It's actually an incompressible flow. This guy on the right here, the free stream Mach number looks like it's about 0.62 or so. So it's definitely not incompressible anymore, but it's definitely not supersonic. So if I look at these guys, the maximum flow velocity in the subsonic case happens about there. In the incompressible case, happens about there, a little bit before the quarter chord. What's different on the supersonic airfoil, on the transonic airfoil rather?
It happens more towards like the back half.
Right. And does the flow actually slow down before before the shock wave?
Nope.
No. It's really, really weird. Like here, we see the flow slowing down pretty much as soon as you get past that hump, kind of the point of maximum thickness. The flow's all slowing down. Here, maximum thickness looks like it's about there, and the flow is still speeding up. So there's something weird going on. And in order to get an idea of what's going on, let's kind of take a step back and look at something a little bit simpler. Kind of like I'm going to pull up a Venturi here, because Venturis explain everything. Here we go. All right, can you guys also see the screen?
Yeah.
Great. All right, just move this over here for a second. All right, so what we got here is your usual incompressible Venturi, right? You guys all built these at some point in fluids. So in your usual incompressible flow Venturi, what happens to your pressure in the throat? Here.
Pressure decreases as velocity increases.
Right. And that's a fairly straightforward relationship. We can plug and chug into the Bernoulli equation all day, get some pretty sweet relationships out of it. Life is good. By the same token, if we looked at this in, actually, I think I have that. Sorry, I just remembered that I purposely made a slide for this. There we go. I knew I had it somewhere. If you look at this in supersonic flow, it doesn't slow down again. As soon as flow exceeds Mach 1, as I open up my nozzle or open up my Venturi, my flow actually accelerates, which is weird, right? If we think of it from a continuity point of view, from incompressible flow, mass flow in is mass flow out, right? As area expanded, velocity had to decrease in order to maintain the same mass flow rate. Here, the velocity is increasing. What the heck? It's weird. But the question is why? So in incompressible flow, how we have been thinking about it, what causes velocity to change?
The shape of the airfoil.
The shape of the airfoil. Okay, how is it related to the shape of the airfoil?
So it has to expand around the thickest part of the airfoil, which causes the acceleration.
Mm-hmm.
And
just go on.
Viscosity and such.
Okay, so viscosity and such makes it stick to the airfoil in the first place. Causes it to move around the body. Actually, causing it to move around the body. You said it causes it to expand, especially as it moves over this kind of first more curved half. Coy also correctly mentions that that expansion is related to a pressure change, and pressure and pressure gradients are what drive flow. So if I have lower pressure up here and higher pressure in front, it's going to accelerate the flow over top of the airfoil in this region. By the same token, I'm going from this low pressure region to this higher pressure region again behind the airfoil. So I'm going to slow down again as I go towards that higher pressure region. It's kind of just the flip side of how we have been looking at this. Does that make sense to everyone? Mm-hmm. You're all on the same page? Great. All right. So because we're going through a negative pressure gradient to here, in normal subsonic incompressible flow, it speeds our flow up. Because we're going from low pressure to high pressure, our flow has to slow down. Great. But the question is, how does the flow know that there's a pressure difference? Or rather, how does that pressure difference propagate through a fluid? And when one way of thinking about it is that is by the analogy of sound, because sound is a pressure wave. It's a relatively low pressure wave, but it is a pressure wave, and it's propagating through a fluid. And last time we worked out exactly how fast as sound would propagate through a fluid at a given temperature, pressure, and density, right? So when we're talking about how fast a pressure difference propagates through the fluid, it propagates at the speed of sound. It propagates at Mach 1 is just another way of thinking about it. So if my pressure difference here, so if I'm sitting on here and I'm a bit of air, and I'm going towards this higher pressure air, the only reason why I know there's higher pressure air here is because that pressure information, if you will, is propagating upstream at Mach 1. If I'm traveling downstream at a very, very slow speed, that's almost instantaneous. I'm traveling downstream to say like Mach 0.1, 2, 0.3. I hear that pressure very, very fast. I know that there's something here, and it has a higher pressure than I do. So it's going to push me out of the way, or it's going to slow me down. In supersonic flow, I'm moving several times faster than anything down here is propagating upstream. So I'm going to get a whole lot closer to it before I hear a thing saying, "Hey, I'm going to push back at you now." Oh, does that sort of analogy make sense to you guys?
Yeah, sort of.
Okay. How does it, and how does it not?
Well, I'm still kind of confused at how when it expands through the nozzle.
Okay.
Accelerating still.
Okay, we're getting there then. The best is yet to come. So, so it takes so I can get going back to what we were saying then, and I promise I will get there in a second. If I'm here, I can travel much further down the airfoil before the downstream conditions force me to slow down. Also, if I think of this kind of in reverse, if I'm traveling down the foil and there's lower pressure back here, I'm now traveling faster than conditions here are propagating downstream. So an upstream effect isn't going to even bother me because I will never know about it. That pressure gradient won't transmit itself to me because I'm moving faster than it. So two things about supersonic flow. So if we look at our supersonic nozzle here, let's say that this is expanding into the atmosphere, same as our subsonic venturi. See if I have a. There we go. It. The how do I say this? So because my flow is moving downstream so fast, when it starts to be expanded in the second half, in the diverging part of this nozzle, the second half, where the nozzle is coming apart again. Its only reason to slow down is because of an upstream pressure difference. eventually it does, and we see we see what could be a shock wave here. But before that, before that shock wave, it does. There's nothing to drive it slower. There's just nothing. There's no reason for the flow to slow down because there's no pressure gradient causing it to do so. As a result, if we think of this from continuity again, so what mass flow rate? It's really hard to draw a dot here. Is constant. Well, if mass flow rate is density times velocity times cross-sectional area, well, velocity is going up, area is going up, area that the flow is going through is going up. What's actually going to change is density. The density of the flow is going to go down in order to balance this whole mass flow rate thing, and it's going to decrease and decrease and decrease, and that's kind of what we see in this drawing here. We start from a relatively high density flow, say like 1.225 kilograms per meter cubed, sea level standard or something like that. As we accelerate, we expect from the isentropic flow relations for our density to go down, but as we expand, it goes down even more, because the flow who doesn't know to slow down, it's not being driven to slow down until the shock wave. So the parameter that has to decrease in order to maintain a constant mass flow rate is density. Does that make a little bit more sense, Ian?
Yeah, it makes more sense now.
Cool. And then how nature kind of reconciles everything is that eventually the flow is going to have to slow down because that upstream pressure information is going to propagate upstream, and nature kind of makes it all work with a shock wave in order to correct the flow properties to what they need to be for downstream. It's one way of thinking about that. So you can only take this. Game of expanding the supersonic flow in order to make it go faster to a point. You have to tune your nozzle really, really finely. So if you ever watch a rocket launch, you'll see the plume of the rocket taking on different shapes. Sometimes it's more spread out. Sometimes it's more focused, and that's all based on the pressure, temperature, and density of the air that the rocket's going through, and where the shock wave kind of occurs, if it does, in the nozzle. So rocket designers actually design their nozzles for certain conditions, and so to get the best performance at certain altitudes. And as a result, you see kind of these different flow patterns depending on where the rocket is versus where its design point is. So that was this is kind of wonky his stuff, but that's kind of the world of compressible flow, especially compressible supersonic flow, and that's kind of what we're going to be jumping into. Specifically, we'll get there in a second. Specifically, we're going to try to look at behavior around shock waves. We've already looked at isentropic flow behavior. So let's see if he can figure out when flow is non-isentropic. So meaning for us at least shocks. We already talked a little bit about the fact that shock waves are entropic effects. So if we're looking at, say, this guy, shock wave here, can say that we can have what's called that our flow on one side of the shock wave is going to be substantially different than the flow on the other side. One side will have a certain stagnation pressure, say, if I could draw a P, that'd be even better. This side will have a different stagnation pressure. If I look at it from my entropy relations from a couple of classes ago, it kind of that's where that kind of pops out of, and it's called because those different stagnation conditions mandate a change in entropy. So we know that we can't use our isentropic relations across the shock wave, but maybe we can figure out another way to work these relations, because we know what has to always be conserved. What in a flow, what is always conserved? What are kind of the three laws we've always fallen back
on? The laws of thermodynamics.
Those are good, but like what does the first law of thermodynamics say?
With energy can't be lost or created.
Right. So it's saying that energy is conserved. Mm-hmm. So that's like one conservation law. What of the properties are conserved? What were we just talking about when we looked at the supersonic nozzle?
Momentum or mass flow rate?
Mass, yes. So mass is conserved. And what else is conserved? You just said it, actually. Momentum. So mass, momentum, energy. Those are always conserved. If they're not conserved, we have problems. Means that there's like 0 point energy coming in somewhere. So mass, momentum, energy. Those things are conserved, and maybe we can build our shock wave relations off of that. But to be a little bit more specific about what kind of shock wave, we set up here for the for like the T38, we have flow coming in to the shock wave that's not normal to the shock. It's on some oblique angle. As a result, we call that condition, which we call that kind of shock wave, an oblique shock. Very inventive, right? Mm-hmm. As opposed to like right here, right in the middle of this shock wave here, the flow is coming in normal to the shock wave. It's coming in at a right angle to the shock wave. We call that a normal shock. As you might imagine, it's a little bit more straightforward to look at because there's just less involved. So we're going to look at a normal shock first. Game on. All right. So here are your two models for it. Again, we're kind of focusing on this latter guy here. We're going to focus on this guy first. So we know that. When how do I want to say this? When we looked at flow, which called variations in flow properties before for incompressible fluids, we said that there was some differential variation in flow properties, right? Like this is a flat plate in flow. There's some small difference in velocity on top, some small difference in pressure on the bottom. Is this ringing any bells? Mm-hmm. Okay, cool. But for a shock wave, the differences aren't small anymore. I mean, that much we can see just by looking at this nozzle. This thin area is a shock wave, and look at the jump in density across that shock. It's humongous. It's humongous relative to all the property variations going on throughout the rest of the nozzle. So we can expect large variations in properties across a shock. So instead of some differential amount, we're just going to have state 1 and state 2. And we'll try to find some relation between those two. We're all, and as you can see, we have here, we're assuming different everything: pressure, density, temperature, Mach number, flow velocity, stagnation pressure, stagnation enthalpy, stagnation temperature, entropy. We're assuming everything's going to change in some way. So let's see how things go. Before we get into this too far, out of the assumptions that we've talked about so far, we've said we can't apply isentropic relations across the shock wave. You can apply it on either side of a shock wave, because there's not a shock wave anywhere else, but we can't apply them across the shock wave. You might think of the shock as an irreversible process. It's that thin region that is the shock. This thing here is a highly viscous film, if you will. So because it's viscous, it's irreversible. Does this mean that it's not? Does this mean that it's not adiabatic too, or might that still be a good relationship for us?
I would think that if it was irreversible, that there'd be, you wouldn't be able to apply the adiabatic assumption.
Why not?
Well, if there's a change in entropy, shouldn't there also be a change in the heat of the system?
Okay, fair. Fair. Based on the entropy relations that we had before, there should be some change in temperature at the very least. But energy is neither created nor destroyed, right? There are ways to change temperature that don't involve dumping energy out of our system. So like if I have my control volume here, this ABCD thing that I'm drawing in reverse order. If I'm looking at my control volume there, I don't have to lose energy from that in order for my temperature to change. I just need to transfer that energy to some other property, right?
Okay.
So we can actually get away with being adiabatic in our little control volume, while even though we're not isentropic and irreversible. And actually ends up being a pretty good assumption for us in this case. So we're assuming adiabatic flow, with the exception of the shock wave. We're also going to assume inviscid flow, both before and after the shock. The shock itself, as said, this guy here, that is a viscous phenomena. The flow on each side, we're going to treat as ice. We're going to treat as ice as adiabatic and inviscid. If it's inviscid, if we're assuming no friction, viscosity, all that, we can also assume that any process that happens is going to be reversible too. So as a result, kind of circling back to where we were before, we can apply our isentropic relations on either side of the shock wave. Again, we just assumed adiabatic and reversible conditions on each side. We just can't relate them through the shock wave. we can't draw a line across the shock wave with one of our isentropic relations because the shock wave is entropic. Okay, so we good on assumptions here?
Yeah.
Sweet. All right, so let's start throwing some math down and see where we can get. All right, so we have our. Ooh, I want to grab that guy. Too. Grab this over here. All right, so. All right, so we have our model here. Okay, so if I'm so if I want to start throwing some math at this, this visible. My first stop is usually like a conservation of math thing, conservation of mass thing, right? So it's like m dot in equals m dot out. Yeah, that's like velocity. It's called density in times velocity in times area and equals density, velocity, area. Anything here that I can relate to each other? Like, is density the same, or velocity the same, or area the same?
The density isn't the same between either side.
Right.
But the area is the same.
Area is the same, right? It's the only thing that is the same based on our kind of normal shock model that we have going on here. We know the density is going to change. We know that velocity is going to change because it's a normal shock, and we've driven and we've drawn our control volume as a rectangle. We know that the area taken up by the flow going through the shock wave, it's going to be the same. So from continuity, from conservation of mass, we can get to this relation that says that rho 1 v1 equals rho 2 v2. Great. All right. So next up, conservation of momentum. So if I do that, this equation is a little bit more complex, and I don't know all the shortcuts yet. So if we do that, we get an equation like this. So this would be conservation of momentum. Be conservation of mass. So conservation of momentum. We get this guy here. Great. What the crap does this mean? So let's kind of just go through term by term again in here. So this guy. So let's start with this guy here. We got a rho v in here. What's that kind of like? What property is that analogous to? Density times velocity.
Mass.
That's called
velocity, not volume.
Yeah.
There. So density times velocity. Momentum, right?
Yeah. It's called really like momentum per unit volume, right? Because it's the density. So that's like momentum per unit volume. I'm multiplying by dv. dv in this case, it's what's called you're integrating across the volume. This v is volume. Wow, I can't write very well here. Again, sorry about the legibility. Hopefully by next week we should be good to go on that front. So I'm multiplying a momentum per unit volume times the volume. I get just momentum out, right? So what does that whole term kind of describe? That let's call that term I have boxed on the far left there. What does that whole term describe? we know that inside of the integral, we have momentum. So we kind of think of you can kind of think of the integral as being all the momentum in the control volume. But what's this ddt thing?
That's if it's steady or unsteady flow.
Okay, so it's kind of like the time rate of change of momentum. If it's unsteady flow, that could change. If it's steady flow, what's it going to be?
That's going to be 0.
Right, and as said, we are looking at steady flow. So this whole term goes to 0. Great, that's easy. This guy here, what's familiar out of that term? Do you see any familiar things inside of it?
We got rho v.
Okay, so we know that there's a density. So we know there's a momentum in there somewhere.
Mm-hmm.
Okay. And then this ds guy, when we last saw that was like the that was like a length term. It was usually like one side of a control volume, and we had flow going through that. So this is like momentum going through a side of our control volume. If you're familiar with like electric flux or magnetic flux, this is momentum flux. It's it's you have some fluid going through a side of our control volume at some rate. Okay. See, and that's not something that any of our assumptions really prohibit, which is a good thing because it means that flow is moving through our control volume. So we're going to leave that guy alone. What about this term here? We have like a pressure and we have like a side of our control volume again. So what does that look like? What would you call it, conceptually speaking?
That'd be the pressure at one face of the side of the control volume.
Sounds like a good deal to me. What would that do? What would that pressure do?
Determine the gradient, I guess.
Yeah. So we have pressure acting on our flow at the edges of the control volume. So from like a conservation of momentum standpoint, this is kind of like the pressure gradient that I'm moving through. Or or in supersonic flow, maybe it's kind of the pressure I need to meet at the back end. Or in our case, it's the pressure that we're going to have to. It's the pressure after the shock wave that's pressing back on my flow. So this term, this PDS term, is called kind of like my summation of forces acting on my control volume or acting on my flow. So that's a good thing to have. It's not something I don't want. It's not something more complicating. It's something that is natural to the flow, and I should expect to have. This last guy, we said that the F is our body force term. So things that act on the entire fluid, you kind of in some uniform fashion or almost uniform fashion, like electromagnetic fields, gravity fields, all that sort of stuff. So we have some like force per unit volume, force per unit mass. We have think of this in terms of like gravity, say. We have some we have some density, right? So that makes it like that when I multiply density and a force per unit mass, it makes it like a force per unit volume, right? Then if I multiply by like a volume, that makes it a total force, yeah. Then I add all those up in my integral. So the same way that pressure times an area, that's like a force. This is also a force. But what have we been saying about body forces? Are we caring about them?
Throw them out the window and let gravity take care of them.
Yes. So for now, we're just looking at flow effects. We're not caring about gravitational effects on the flow. We're just looking at the flow itself. So all we got left are these guys here. So if I'm looking at those and I consider my integral, when I integrate like say like x back to x, say I do it from like x1 to x2. What I get out is what, like 1/2 x squared from x1 to x2, right? Something like that. This might seem dumb. I promise I have a point. So when I substitute those in, I get something like this, right?
Mm-hmm.
Cool. So really, an integral is just moving between two states. In this case, my states are x1 and x2. Up here, I have I have integrals here. Well, I'm moving between state 1 and state 2. So I'm just moving between those two two states, those two sets of properties. So when I write this puppy out, I'm going to get something that looks a bit more like this. Let me just try to do this in a little bit more legible way. So that first term there is what? Density times velocity times an area, ds. So it's like moving from state 1. If I say that entering my control volume is negative, leaving it is positive, then I have a negative velocity coming in, multiplied by my area, and that's times u1. So this is exactly what's in this left-hand what's in this left-hand integral, right? So it's like a rho a velocity times a perpendicular area times a velocity again, right? That's literally just whatever's in my integral there. Except I've integrated my ds because it's now not a differential area; it's an area. It's a complete side of my control volume. And because it's an integral, I got my two states. So U2A, U2. And I can do the same thing for my pressure term. So negative pressure on state 1 times A plus pressure state 2 times A. And make that a little bit bigger. Great. So there my integral is written out there. I crunch some math with. I can crunch some math with this. Whoops. and get something that looks like simplified form anyhow, something like this. Which looks an awful lot like Bernoulli, right?
I would say so.
Which is kind of cool. Like, it makes intuitive sense that just because Bernoulli, which we stopped using it because it was maybe because we made assumptions of incompressible flow when we have applied it. It doesn't make sense that it should go completely out the window. There should be something of it floating around, and we can kind of see that here because it's pretty much the same gig, except we have density change in it now. Sweet. So this here is what we're going to use for our expression of conservation of momentum across a normal shock, because that's what we just integrated between. Because we know that that momentum is conserved across a shock wave. So this equation will hold across a shock wave. Same way that up here, this rho 1 v1 equals rho 2 v2, like that will hold across a shock wave. We can also throw, our what's called the energy equation that we made before at this, because energy is conserved across a shock wave as well. So if I want to kind of complete my cadre of what's called mathematical models, I can kind of throw that in here too. And from before, our conservation of energy equation said something like this, where the what's called, say, like the enthalpy state 1 plus the velocity squared over 2 from state 1, so kind of our kinetic energy equals our stagnation enthalpy, or some constant. Well, I want to write out the other half here. Well, H2 plus U2 squared over 2, they're all equal. So that's our conservation of energy energy. Now, when we get here, you might say, wait a second. You got, let's see, 1, 2, 3, 4, 5 unknowns floating around here, and three equations. What the heck? Don't forget that we also have our equations of state, or our equation of state. So that'd be like P equals rho RT, because we assume that this is a perfect gas, and we also assumed a calorically perfect gas. If I can write enthalpy relations. So we can also say that say things like enthalpy is equal to our specific heat times temperature, or if we want to if we want to really dig into it, we can also make a relationship with our internal energy as well. So we have enough equations to solve for all of the variables here. If we ignore this guy, because it's kind of wrapped up into enthalpy, we can say that we have 5 equations and 5 unknowns. We can make this thing happen. Awesome. Are we all on board with this? Are there any questions at this point with how we put these equations together and kind of what they mean?
No.
All right. Sweet. All right. So before we start throwing these things at our what you call at our shockwave flow, there's one other thing that I want to touch on, namely, in order to kind of how do I want to say this? In order to relate flow properties to Mach number, which is really the important thing that we want to do here. We want to be able to say, I'm flying this fast. Tell me what the flow is going to be doing. And that's kind of what we looked for with airfoils in incompressible flow, right? The kind of the coup de grace for us was when we finally came up with with an expression that said, you're flying at this angle of attack, you get this much lift. Bam, done. We don't really have to worry about vortices or any of this other stuff. By the same token, be really nice if for normal shocks, if I'm trying to find out what's going on back here, if I just know how fast I'm flying, what Mach number I'm flying at, since the speed of sound ends up being really, as we've seen, ends up being really important. If I just know what Mach number I'm flying at, it'd be awfully nice if all of my downstream properties were in terms of, could be found in terms of Mach number. So before we get too far into this, let's see if we can get a relationship between Mach number and some of our conservation equations, because right now they're all in terms of flow speed, which is nice. But again, I said the important term is going to be Mach number. So let's get it on. So let's erase the rest of these. Cool. All right. So starting from our equation for the conservation of energy, we know that enthalpy is same thing as specific heat times temp times temperature. So I can throw that around. Maybe and let's see if we can simplify this equation a little bit, but to get more things that are the same, especially because I know that Mach number is related to speed of sound, right? And speed of sound is defined as what? What was our expression for that?
The square root of Yep. That's all I got. I got square root.
Okay.
Is there temperature in there?
Say again, please.
Is the temperature in there?
It is.
Flow?
Yep. As well as the gas, as well as the gas law, as well as the gas constant for the fluid, and gamma, the specific heat ratio.
Mm-hmm.
So that's our speed of sound. So if we can get this to pop up in here, we can get Mach number, right? Because Mach number is just flow rate over the speed of sound. So if we can get speed of sound to pop up, maybe we can make this work. By making this substitution, all that gets us that gets us the temperature. And when we were deriving our isentropic relations, we said, hey, we can define our specific heat in terms of a specific heat ratio and our gas law and our gas constant. So we can get some gammas out of this. We can get temperatures out of this. It seems like we should have all the kind of the building blocks for getting speed of sound and thus Mach number out of this. So let's keep this rolling and see where we get. So let's make that substitution in here. Gamma R over gamma minus 1. Oops, if I put in that the right way, it would help. Okay. That's there. Okay, we're getting closer. But we still need to like divide by this at some point in life, right? So I'm going to look here and say, well, first of all, there's like gamma RT and the gamma RT, right? So that by itself, I can just say right off the bat, that's the speed of sound that's the speed of sound squared prior to the shock wave, and the speed of sound squared after the shock wave. Yeah. So now I just have to. So now I just have to get that I just have to get to. Now I just have to get that underneath of my flow rate, and I can get Mach number. But it's going to but that's going to end up being a little tricky, right? Because when I divide by these things, they're going to go everywhere. So let's just look at one side of the shock wave at a time. And let's just look at the left-hand side, say. So I'm going to grab that and bring it down here. So this guy, if I'm looking at, if I look at everything on the same side of the shock wave, what if I isentropically slowed my shock wave, slowed my flow down so that the flow speed is 0? My energy equation would be like this, right? I'd have whatever flow is on this side when it's traveling at some speed. And then I have this side, which is like my stagnation condition, which kind of matches back up here with my, with how I made my energy equation. Y'all following?
Mm-hmm.
Okay. So I got I got that now. So if I how do I want to say this? So I can play that game, but that doesn't get me all too much. What if I go the other way? What if instead of slowing the flow down, what if I speed it up instead? What if I speed it up? What if I isentropically speed the flow up to Mach 1? So that's now the speed of sound. We're going to call this my star condition. And since these two are the same, there we go. So the flow's traveling at this starred condition. It's been isentropically accelerated to the speed of sound. This might actually be able to work out for us a little bit easier, because we'll get a Mach, because we know that we can get a Mach number out of this is on both sides of the equation, instead of still having a speed of sound in here somewhere that's kind of loose. So let's see what we can do. I'm going to how do I want to do this? I'm going to divide through by. Sorry, I lost my notes here. Oh, that's what I need to do. If I divide through here, do a little bit of rearranging. So I'm going to compress because we're almost out of time. I can get I can cudgel this equation into something that looks like this. Where where I have my speed, where I can kind of simplify things into this expression for that 80 for that adiabatic condition that goes out of the condition where I've adiabatically and isentropically increased my flow speed to the speed of sound. I can get that expression as a constant. And next time we'll talk about that a little bit more and what it does for us, because we're presently out of time. But are there any questions how we got to here?
Nope.
Okay. Well, that's all I got for today then. Thanks for stopping by.
Yoki.